today we're going to be talking about magnification. This is one of the most commonly asked math type problems in IB biology, and so I thought it would be helpful if we worked some sample problems together today. Okay, so first of all, when would we encounter these types of problems? Primarily when we're talking about microscopes and microscopy, and anytime that we're dealing with either a light microscope, an electron microscope, or things of that nature, anytime something has to be magnified. So, number one, what is the total magnification of a microscope with a 15, and the X just stands for times, right? So the ocular lens is magnified by 15 times, and a 40 times objective. All right, so what you're going to do here is, first and foremost, in order to get total magnification, you're going to want to take the ocular and multiply it by the objective. Okay? So let's see if I can do that right here. Okay, so what you're going to do is you're going to take 15 and you're going to multiply times 40. All right, and what that should give you is 600. And so what you'll put is you'll put an X right there, and that just stands for 600 times. So the total magnification of that microscope image that you're looking at is going to be 600 times more magnifying than it would be by the naked eye. And so that's what we're doing. When I say the ocular refers to your eye. And so when you're looking at a microscope, it either has one tube to look through, or it'll have two, one for each of your eyes to look through. And that part is called the ocular lens, and it always has its own magnification on it. And then the ones at the bottom that can spin have separate magnifications on them, and they are called objective lenses. And so they vary in strength, and so you have low power, medium power, and high power on a regular compound light microscope that you would encounter here at school, or even in most college programs. And then an electron microscope is a different type of microscope that is much more advanced and in depth and all kinds of stuff. Okay. Number two, a student determines that the field of view. So that means when you're looking through the ocular lens, what you can see at the bottom. So number three, it's giving you like a diagram of a field of view. And so what you're seeing in that circle is your field of view. Okay, so the student determines that the field of view with I always like to underline my numbers so that I know where to look. With a 10 times ocular and a 4 times objective is 2.5 millimeters in diameter. What is the diameter of the same ocular and a 10 times objective? Okay, so for this one, we're going to work it a little bit differently, and that's okay. So the best way to do this is to start talking about what we know and what we don't know. So first things first, you're going to want to take that 10 right here and multiply it by that 4, and then you'll get your low power. So let's do that. So 10 times 4 is 40, okay? And that's going to be your low power. And then we will take this objective here, and it will be the ocular times the objective. So there's 10 times 10, and you get 100. And so that's going to be your high power magnification in this problem, okay? And then it also asks you about diameter. So it gives you a diameter, and then it asks you what the diameter of the field of view would be with this magnification now. So how do we set this up? So what you'll do after you've done some basic math is you will take that low power Okay, so you're going to take that low power. Here's 40. That's our low power magnification. You don't have to put a unit on magnification. The X is just a placeholder to let you know it's that number times magnification. So it's just a placeholder. So we've got our 40, and you're going to want to multiply that 40 by the original diameter of the field of view on low power. So 2.5 millimeters. And then you're going to need to divide that by your high power magnification. Okay, so this is how you set that up. And then, and then by the time you're done adding all of this together, right, in a calculator, which you are allowed to have on the test, this will give you 1 millimeter. Okay, and that is your diameter of the same ocular and objective and everything. So that's going to be the diameter. And that's how you solve that problem. We'll try to work many more of those so that you can get the hang of it. But it's always going to be your lower power times the diameter divided by your higher power. And then that's how we get the diameter. All right, let's work a more advanced problem on number 3, okay? All right, number 3. If the amoeba is being viewed with low power, so here I go again. I need to highlight and underline. Okay, so if the amoeba is being viewed with low power with a 4.5 millimeter field of view, then what is the estimated longest length of the organism? And then you need to show your work. And in other places, they call it show your working. Isn't that funny? Okay. So, first things first. What you're going to want to do is, okay, it's odd. So, in order to determine the length of the organism, it tells you in the practice problem, the one, that it's on low power, which will come in handy later, but 2, that your field of view is given to you by 4.5. So you know that's going to go somewhere in the problem, right? So you just write that down here, 4.5 millimeters. Okay. Now this next part's kind of weird. So you look at the field of view because it's this area here. This whole thing right there is your field of view, the whole white part. And what you're going to do is tell me how much of that field of view you would estimate that amoeba is taking up. So from here to here, you always pick the longest parts, okay? So how much of the field of view is it taking up in diameter? And it's literally a pure estimate. How many amoebas do you think it would take to get all the way across your field of view? In this case, today as a class, we estimated that it would take about 3 of them to go all the way across. So now what you're going to do is this amoeba takes up about 1/3 of your field of view. And so I chose to multiply times 0.33. The other kids today decided they would prefer to just divide by 3. It's totally up to you how you want to pursue that. I prefer to multiply. So I'm going to multiply. You can also multiply by 1/3 if you would prefer. So you can multiply by 1/3. And what ends up happening is that gives you 1.5 millimeters. And that is your estimated longest length of the organism. So we scroll on down to 4, and what it's telling you is we're going to be working with this exact amoeba again. So it's a 2-part problem. So here is the same amoeba as in number 3. Add a labeled scale bar to the drawing, then determine the drawing's magnification. Okay, let me shrink my face down so you can actually see our space. There I go. All right, so let me get my ruler. All right. Okay, so first and foremost, what you're going to want to do is make a scale bar. So you take a ruler, which y'all cannot see my ruler. I understand that. Okay, let me get my stuff in the right place. All right, and what you're going to do is you're going to go from one edge of it. It's hard to do on this computer. And you're going to draw a straight line with the ruler all the way to the other edge of it. And then you take that ruler and you make, see if it'll let me do this. And you make little, oops, I need to erase that. Take that little piece off. Okay, and you make a straight line. It's hard to do on an electronic piece of paper. Pretend that's straight. Okay. There we go, because it is just not working. And so you've made this scale bar from the longest end to the longest end of the amoeba. Okay, and you know from this problem up here that the distance of the amoeba, you've estimated and calculated it to be 1.5 millimeters long. So this whole amoeba is supposed to be about 1.5 millimeters long. So now what you do is you're going to take your ruler and you're going to put it on the amoeba and you're going to measure effectively from the longest part of the amoeba to the other side of the amoeba. Or you can choose to measure your scale bar because they should be the exact same length. So when you take a ruler, always use the metric side, first of all, and then measure your scale bar from end to end that you just drew. And on ours, we found it to be, I'm just going to write it off to the side for scratch work, 73 millimeters. We choose to always work in millimeters right now because a lot of stuff coming up when we start calculating reverts back to millimeters in order to make it easier and functional in the calculation. So instead of centimeters, we leave it straight up as millimeters. Okay, now the cool thing is, in order to do this, if you need magnification, they came up with something called the I am triangle. And so, whoop, there we go. And it looks like this. And there's an I up here, and an A down here, and an M right there. And what this is the exact set of equations that you will use to find just about every solution, and it's so great. So in this case, we're looking for magnification, the M, that's what that stands for. And so what we need to do is we need to take the image size and divide it by the actual size. And so what that looks like is we take 73 millimeters and we divide it by 1.5 millimeters, okay? And that's going to give us 48.67, 67 millimeters. Okay, now because of significant figures and things like that, you can only round to 1 sig fig. And so that 48.67 becomes 50 times, or I'm sorry, not millimeters. Those cancel out. 50 times the magnification. And so it asks you to determine what the magnification is of the drawing, and you've just done that here. The magnification of the drawing is 50x. Hopefully your paper is a little more organized and cleaner than mine. It's hard to do on an electronic piece of paper. Okay, so that's the beginning of that. I want to work one more with you, so we're going to skip to the back and try to solve one on the back together. All right, so this cell is drawn 2,000 times larger than life size. Determine the actual size of the cell and add a labeled scale bar. Okay, great. So the first thing I want you to do is to draw that I am triangle. It's always helpful to start there. So I am. All right, so what are we given then? Let's talk about that. We're given magnification. So we have that. And it's asking us to determine the actual size. So we need to find this. So you know automatically that with our scale bar, we will then have to come up with the image size, okay? And we are given the magnification, so let's get started. So once again, you're going to take your ruler. Mine's clear. I know that's not helpful. I prefer clear rulers because it's easier to see the images on the back. And you're going to take your paper, okay, and you're going to put this down with the metric side, and you're going to draw a scale bar. So let's do that together here. Okay, so where am I at? Right there. So we're going to draw it. And then once again, I'm just going to have to do my best to make a straight vertical line with this digital paper. Okay, and that's our scale bar. And then when you measure it on the actual paper, it measures 57 millimeters. Okay, so don't write that on the scale bar. Write it off to the side because that's just the image size. So 57 millimeters. And according to our IM triangle, what we will do now is take that image size and divide it by the magnification. Okay, and when you do that, you get 0.0285 millimeters. And with significant figures, you only get to keep one significant figure. And so your answer is actually 0.03 millimeters. And that is the actual size. And so that's why you go back down to your scale bar and you write 0.03 millimeters. What that means is the actual size of that cell is 0.03 millimeters. And that lets you know how zoomed in it is. It makes it difficult online to try to do this because if you try to measure how your screen and the length of the cell on your screen, it's a lot different than how magnified it is on my paper. And so these things are best to print off. If you're one of my digital students, print them off and then do it on paper. Otherwise, your answers are going to be all kinds of messed up. And on your test, on your actual end of year test, right, everything for this type of problem will be on paper, and it'll have to be able to be measured and calculated on paper so that we all can get the same number. Because if it's digital, you guys have your computer screen set to zoom at different magnifications, and so we would all have different answers if it wasn't on paper. All right, so those are all the practice problems I'm going to work on this video. Try the other problems on the worksheet, and then email me if you have any questions at all. All right, good luck.